Hi, folks. Today we're going to take a look at our 12.7 cylindrical and spherical coordinates. But before we do that, let's talk a little bit about graphing in R2. Okay, so graphing in R2 is something that you've been doing for quite some time now. And we've learned a few different ways to graph in R2. And I think the most common way that we have been graphing is having an X and a Y axis and then plotting points accordingly. So, for example, if I had the point 2 comma 1, I would go from my center over 2 and then up 1, and this would be my point P, right? And we know that we've got sort of positive X in the right direction, positive Y in the up direction. And that was all fine and good. But as you started to learn more about different kinds of functions, different kinds of expressions, and their relationships between each other, one thing that maybe you noticed was it actually became a little bit harder at some point to go ahead and draw things that were maybe round or describe things that were round in R2. Okay. And so at that point, maybe you recall starting to see graphs that look kind of like this. Right. And it was based on this idea of the unit circle where we start counting our angles from the positive x-axis, and we call that angle theta. And then however many radii we go out, that was our R component of our coordinate. And so if we were to think about the point, let's say, let's give it a different name. Let's say point Q, and that was, let's say 2 comma pi over 4. Then the way I would do that, I would go to the angle pi over 4, and then I would go 2 circles out in that direction, right? So I put somewhere like around here, and we would call that point Q, right? And so what we have on the left-hand side, we call this the rectangular coordinate system. You might have also heard this called the Cartesian coordinate system, right? But rectangular and Cartesian represent the same thing. It's just our regular XY. But then when we talked about the thing with the roundedness, this was what we called a polar coordinate system, okay? And so we took these two as different ways of describing points in R2. But when we move up into R3, it turns out we can sort of start to combine these two, or maybe purely be in one or purely be in another. Okay, so here's what I mean by that. I'm going to take a look at the graphic organizer that you've got. All right, let me zoom in real quick so we can see on this graphic organizer, we have the three main coordinate systems for graphing in R3. Okay, the first one is what we call the rectangular system. The second one is what we call the cylindrical system. And the last one is what we call the spherical system. And all three of these are just different ways of finding points and describing curves and describing surfaces in R3. Okay. The first one is our rectangular. Okay. And again, we can sort of use this word rectangular and Cartesian interchangeably, but it is very similar to our XY. We are just adding a Z component to that, right? So if I want to graph this point P, that is XYZ, X represents the distance along the Y-axis, X represents the distance along the x-axis, Y represents the distance along the y-axis, and Z represents the distance along the z-axis. And so we go like out along the x, we go out along the y, we go out along the z, and that's how we end up with point P. Okay? All right, so let's move on to cylindrical. At some point, people were like, well, if our base plane like is XY for rectangular, why couldn't we swap that XY out for an R theta plane? And so this is going to be helpful when we're describing cylindrical surfaces. But we basically take the same idea where now we're looking at going out to a particular angle, theta. Theta is our angle of rotation from the positive x-axis. Okay. And then from the center, we count out however many radii we have of circles. That's our r. And then the z is just like the z component in the rectangular one. I'm just going up or down that z-axis, okay? So that is what we call the cylindrical coordinate system. And last but not least, there's one that we call the spherical coordinate system. And this spherical coordinate system takes the idea of distance from the origin, but opens it up to be in any direction from that origin. So we call this letter rho. Okay, let me clarify. This is the Greek letter rho. It is not P. Okay, it's different. It is rho. And rho represents just the distance from the origin to any point in any direction. Okay. Now, the direction, though, that's where the theta and the phi come into play. So, our theta is going to be the angle of rotation around, excuse me, from the z-axis, okay? And so when we're going around the z-axis, we're thinking about it kind of like the theta. It's from the positive x-axis, okay? So saying the angle of rotation around the z-axis is the same thing as saying we're starting from the positive x and we're moving out in that counterclockwise direction, okay? So this theta in the spherical is the same as the theta in the cylindrical coordinate system. And lastly, we describe this last angle phi, right? This is phi, as the angle of rotation down from the positive z-axis, all right? So in other words, we're saying here's our z-axis and we're counting down a certain number of degrees. That's going to tell us the direction in which our rho, our distance from the origin to the point, is being counted in, okay? So lots of letters. Who knew we needed so many letters? But in addition to sort of knowing these coordinate systems, it's going to be really helpful to convert between the coordinate systems, okay? So I don't want to talk about these too much in detail. You can look at them on your own graphic organizer, but I've included if you're starting from rectangular, how do you get to cylindrical? How do you get to spherical, okay? If you start in cylindrical, how do you get to rectangular? How do you get to spherical? And if you're starting in spherical, how do you get to rectangular and how do you get to cylindrical? Okay, so knowing these conversions will be really helpful, but we're also going to get a chance to practice all the algebra that goes into converting things, sort of being clever so we can make some of these conversions pop out even when it seems like it's really algebra heavy. Okay, so this is where we're going to stop the first video. Come on back for the second video where we're going to go through examples 1, 2, and 3, and we're actually going to practice converting the coordinates. If you want to go ahead and practice this first and then come on back and check your answers, great idea. Otherwise, I'll see you in that second video.